The topic of my presentation is Strength and Microstructure of Alkali Activated Phosphorus Slag Binder, Effect of Activator Type or Dosage, and the Phosphorus Slag Chemical Composition. As we all know, alkali activating materials have been widely considered as a promising alternative binder to Portland cement. But most precursors of alkali activating material are aluminum-rich material, such as fly ash and blast furnace slag. Phosphorus slag is the waste produced in the production of yellow phosphorus by electric furnaces. Similar to blast furnace slag, phosphorus slag is mainly composed of amorphous phase, which is expected to have a potential hydration activities. But compared to blast furnace slag, phosphorus slag has a lower aluminum content. Although different kinds of precursor with different chemical components are well investigated, such as blast furnace slag with high calcium content and fly ash with low calcium content, the precursor of low aluminum content has not been fully studied, which makes phosphorus slag become a suitable material to explore the low aluminum alkali activated system. In this study, two different quenched granulated phosphorus slag was used, marked as P1 and P3. Few crystalline phases was found in the phosphorus slag, which means the chemical composition determined by XRF are almost the chemical component in the amorphous phase. This means two kinds of phosphorus slag are consisting of similar amorphous phase with different calcium to silica ratios. P1 has a higher silica content while P3 has higher calcium content. Sodium hydroxide solution marked as N and water glass with 3 modulus 1, 1.5, and 2 were chosen to activate the phosphorus slag. Sodium oxide to slag weight ratio were 4% for all activator. The compressive strength differs when different phosphorus slag was activated. When the P1 with lower calcium content was activated, different activators exhibit similar 28 days compressive strength, while P3 exhibit a higher compressive strength when water glass was used as activator compared to sodium hydroxide. When water glass was used as activator, compressive strength of P3 is higher than P1 at 28 days. This illustrated that water glass is more suitable for phosphorus slag with high calcium content. Besides, P3 also exhibits a fast strength development in the early age due to the higher calcium content. Up to 28 days, the compressive strength shows no significant difference between two slags activated by sodium hydroxide, but P3 shows a faster compressive strength development than P1 due to the higher calcium content, increase the alkalinity of P3. Isothermal calorimetry shows the early reaction of alkali-activated phosphorus slag. When water glass was used as activator, the induction period of P3 is shorter than P1, and the broad exothermic peak, followed by induction period, is intenser than P1 when same activator was used. When sodium hydroxide was used as the activator, little difference of the induction period and the exothermic peak was found between two different phosphorus slag. The short induction period of P3 in water glass system can be explained as the higher calcium content provide a higher self-alkalinity to accelerate the dissolution of P3 and thus shorter the induction period. For P1, The lower calcium content means although there is enough silicate for nucleation in water glass, the lower alkalinity limits the early dissolution rate and thus slow down the nucleation rate. While sodium hydroxide is a stronger activator, which provides sufficient alkalinity for early dissolution, the exothermal peak is less different between two phosphorus slag when sodium hydroxide was used. Accumulative heat shows the same trend as exothermal peak. Sodium hydroxide releases more heat in P1, while water glass releases more heat than sodium hydroxide in P2, especially modulus 1. This is consistent with the Strand's result. Sodium hydroxide has better activated effect in P1, while water glass is better in P3. X-ray diffraction shows the product in alkali-activated phosphorus slag, different from CaSH gel in common alkali-activated materials. The main product in alkali-activated phosphorus slag is CSH due to the low aluminum content. For both two phosphorus slags, the crystallinity of CSH in water glass system is lower than sodium hydroxide system and decreased with the increase of modulus. Less crystal phase diffraction appeared when modulus increased. This is due to a higher alkalinity increased the crystallinity of CSH. Hydrotoside is second phase in common alkali-activated materials, but due to the low aluminum content in phosphorus slag, less hydrotoside was found in the binder, especially in the water glass system. This can be interpreted as the lower alkalinity of water glass result in a lower pH of the early binder solution and decrease the crystallinity of hydrotoside. While sodium hydroxide and high calcium provide a higher pH in the solution, which leads to the high crystallinity of hydrotoside. Nuclear magnetic resonance was used to analyze the chemical environment of items. After 28 days curing, three new intense peaks can be observed: Q2, Q21 aluminum, and Q1. The pattern showed that for P1 with higher silica content, the chemical environment of silicon is less affected. For P3 with lower silica content, the higher silica concentration in the activator is, the less Q1 and the more Q2 will be. The alkalinity of the solution almost makes no effect on silicon chemical environment. This can be explained as more silica participate in forming CSH and thus increase the content of Q2. While the alkalinity only affects the dissolution rate of phosphorus slag and the nucleation rate of CSH, but doesn't affect the chemical bond structure of CSH. Above all, this study shows that sodium hydroxide is more effective for low calcium content phosphorus slag, while water glass is more effective for high calcium phosphorus slag. The alkalinity of the solution and the phosphorus slag, or we can say the calcium content of a phosphorus slag, determine the heat release rate, while total silica content determine the total heat release. The main product in alkali-activated phosphorus slag is CSH, which is different from common alkali-activated materials. High alkalinity of the solution increase the crystallinity of CSH and the hydrotoside, but the alkalinity doesn't affect the chemical environment of CSH. Total silicon content of the activator and the precursor is the main factor that determine the silicon chemical environment. Thanks for listening.